Hi, video number 20 is going to be the very first video where I talk about a super important concept called the mean or expected value of a discrete random variable. We will be finding the mean or expected value in the same situation as video number 19. We're counting the number of heads when you flip an unfair coin 3 times. It's a context taken from this book by Leonard Asimov and Mark Maxwell, exercise 3-7. We did a modified version of that in video number 19. Here I'm extending the problem, doing extra to talk about these concepts. So we have a loaded or unfair coin that has a probability of heads equal to 0.6 on any individual flip, not 0.5. So it's not fair, okay? This is not what you would typically expect. We want to flip the coin 3 times and count the number of heads. The random variable, capital X, is your discrete random variable denoting the number of heads. It can be 0, 1, 2, or 3. In video number 19, we found the probability mass function, PMF, called little f of x, whose values are given in this table that you see here. What does it represent? Well, for example, when little x equals 2, you get little f of x, little f of 2 equaling 0.432. That means the probability that capital X equals 2 is 0.432. Okay, and that's the highest probability. That's the highest chance. We also emphasized in video 19 that technically little f of x is defined for all real x, just equals 0 for those other values of x. All right, what do we want to do in this video? Part A, in various ways. I'm being purposely kind of vague. I want to try to make sense out of what we're doing here. That's why I'm being vague. We want to find this theoretical mean, or average number of heads in this case, in the long run if you did the experiment of flipping the coin 3 times and counting the number of heads over and over and over again. There's a special symbol that we use for it. It's this thing right here. It's a Greek letter. It's called mu, which makes me very happy because it kind of looks like an M and it kind of looks like a U, so we call it mu. Isn't that great? That's one symbol for this mean or average number. And what should it equal? Well, again, think about it. Imagine doing this experiment over and over again, hundreds or thousands of times, getting a bunch of 0s, 1s, 2s, and 3s. The ordinary way to average those is just to add them up and divide by the number of times you did the experiment. You wouldn't necessarily get a whole number. You could get, say, 1.4 or 1.72, etc. You don't get any of those. You might even want to think about what you might get ahead of time here. That's what this theoretical mean or average should be. Note this quantity has a different name. It's also called the expected value of x. And it also has a different symbol. It's also written e of x. Okay? This is really important. You're going to see these symbols and this terminology over and over and over again as you continue studying probability. In part B, I want to generalize it. I want to write down the general formula for the mean or expected value of an arbitrary discrete random variable x. Okay, so we'll see if we can take what we do and generalize it. All right, so what do I mean by various ways here? Well, what's the first way? Think of it intuitively in terms of, what would happen if you flip the coin, say, 100 times, and if it was a fair coin? Well, what would you expect for the mean? By the way, there are a lot of puns when you start talking about these things with the words expect and mean in them. We are also going to talk about the geometric meaning of these things with Mathematica at the end. Well, if the probability of heads on any individual flip were 0.5, you'd expect around 50 heads, right, out of 100? 100 times 0.5 is 50. Not necessarily that you get exactly 50. You could get 48 or 49 or 51 or 52 or maybe even 57. But generally speaking, you would expect it to be close to 50 out of 100. If the probability of heads is 0.6 instead of 0.5, you should expect around 60% heads, 60 out of 100. So it seems like we should take the number of flips or trials times the probability of heads on each trial. So mu, or e of x, is n times p, where n is the number of flips, or in general, number of trials, and p is the probability of heads on each flip, or in general, the probability of success. Now I'm using these words because I'm trying to emphasize that x actually is a very special kind of random variable. It's called a binomial random variable. Whenever you have a certain fixed number of trials that are either a success or failure, the probability of success stays constant on each trial, on each flip in this case, and the trials or flips are independent of each other, so that we can derive the formula that we derived in the last video, then this will give you the mean. In this case, it's not 100 flips, it's 3 flips. Probability of success is 0.6. The answer is 1.8. That is going to be the mean. Okay? I hope that makes intuitive sense. But again, it is only because it is since x is a binomial random variable. That's a special name. Binomial random variable. This does not work in general for an arbitrary discrete random variable. Okay? That's kind of why this situation is the simplest to think about, is because that should make intuitive sense. But what would work more in general? Okay? Well, we can still imagine what's going on here. Let's imagine that we run this experiment 1,000 times, where one run of the experiment is not 1 flip, but 3 flips. Flip it 3 times, count the number of heads, write it down. Maybe you get a 2 the first time. Do it again. Flip it 3 times, count the number of heads. Maybe you get a 3. Continue doing that. Let's say 1,000 times. What would you expect for the mean in that situation? You're going to get a bunch of 0s, 1s, 2s, and 3s. How many of them? 1,000 of them. You're going to divide by 1,000. What goes in the numerator? Look at those probabilities. Probability of getting 0 heads on any one run of the experiment is 6.4%. What's 6.4 of 1,000? 64. There'd be 64 zeros. 64 times 0 is the same as 0 plus 0 plus 0, etc. 64 times, which of course is 0, so I don't have to put it in there, but I'm trying to emphasize something. How many 1s would you expect? 288, right? 28.8% of 1,000 is 288. Again, not that you get these numbers exactly. You could definitely get 287 ones or 270 ones for that matter. But based on these data here, you would expect it to be somewhere close to 288. So let's just go ahead and pretend it is 288 ones. 288 times 1. About 432 2s and about 216 3s. That should be the mean as well. Is it? Do we get the same answer? We do. You get 0 plus 288 plus 432 times 2 is 864. 216 times 3 is 648 over 1,000. This does end up being 1,800 over 1,000. I'll go ahead and check it. 288 plus 864 plus 648. 1,800 over 1,000. 1,800 over 1,000 is 1.8. We get the same answer. Isn't that amazing? Okay. There's the third way to think about it. And that third way is going to be the main way you want to think about it in general, and it's going to be the way we're going to generalize it. Take this fraction and split it apart into pieces. How? How about this over this, plus this over this, plus this over this, plus this over this, and then break those fractions apart. Put the 0, the 1, the 2, and the 3 in front. Here's what I mean. Mu, the expected value of x, could be written as 0 times 64 over 1,000 plus 1 times 288 over 1,000 plus 2 times 432 over 1,000 plus 3 times 216 over 1,000, which in decimal form could be written as 0 times 0.064 plus 1 times 0.288 plus 2 times 0.432 plus 3 times 0.216. I'm adding the values of x times the corresponding probabilities. And that's the formula that generalizes. You can check this does end up equaling 1.8 again. Check that on your own. For part B, that's how we generalize this to an arbitrary discrete random variable. For part B, In an arbitrary situation, we add up, use the summation symbol, the values of x times the corresponding values of f of x. What does the sum range over? Okay, you could just maybe put an all x here. It would be understood if you do that, based on the fact that this is discrete, that this would be a sum that converges. In this case, all x where little f of x is positive, it includes only 4 values of x, 0, 1, 2, and 3. You could also emphasize all x where little f of x is positive. But it's got to be a convergence series in general, and it's got to be, in fact, a countably infinite sum, where I won't say what that means when you're talking about discrete random variables, either finite or countable. Let's end the video by looking at Mathematica, as we often do, and looking at some graphs here. So as I showed you in the last video, number 19, here's a way to get the PMF into Mathematica, although you've got to use PDF, probability density function in Mathematica. That's a name that's best reserved for continuous random variables, but you've got to program it this way in Mathematica. Notice the binomial distribution. The 3 is the number of flips, the P is the probability of heads on any given flip, which is 0.6. And each of these 3 sums is a different way to get the mean of 1.8, although it's written as 9/5 with that sum. When you put a decimal in there, you get a 1.8. Here I'm just emphasizing that Mathematica knows that the value of this function is 0 except when x is 0, 1, 2, or 3. So I can go from minus infinity to plus infinity. I still get the same answer of 1.8. How could we give meaning to the mean? Geometrically or physically interpret it? You can do it this way. Here's the graph of the PMF, and I can change the value of P, the probability of success, and you see the PMF changing. The blue dot is the location of the mean. When P was 0.6, as it was in our problem, it's at 1.8. That blue dot is at 1.8. If P were 0.5, if it were a fair coin, then the blue dot is at 1.5. I hope that makes sense. And that is kind of like a center of mass. If you imagine these vertical lines that are the places where little f of x is non-zero as representing like thin wires that have a certain mass to them, and say a constant density for all of these things, the blue dot is at the center of mass of those things in the x direction. You can see when most of the mass is near 3, the blue dot is near 3. When most of the mass is near 0, the blue dot is near 0. And when the mass is basically symmetric, the blue dot is close to 1.5. Another way to visualize this is to imagine the probabilities as being actual masses. So I made the red dots here purposely different sizes proportional to the probabilities, the masses, in their size. And you can see as I change the probability of heads, the center of mass changes, okay? That's kind of a nice way to visualize the blue dot as the center of mass of these 4 point particles. Thanks for watching.